So we're in the second lecture on the second law of thermodynamics. We covered a lot of ground. It's a little abstract, maybe a little challenging to grasp, but it's very, very foundational and very important. Let's just continue to go through it. This was a difficult discussion. Let me just summarize the net result of this discussion last time. Is that if you have a reversible heat engine or a reversible cycle operating between two thermal reservoirs, it could be a heat pump or refrigeration, but often we think about a power cycle. Then the ratio of the heat transfer to the low temperature divided by the heat transfer to the high temperature is equal to the ratio of those Q's, or Q dots, either in kilojoules or kilowatts, is equal to the ratio of absolute temperatures, TL over TH. That's kind of a big deal. It is a very big deal, and that will provide a foundation by which we get the very abstract new property called entropy. One of the things that we use for it is for a power cycle, we get that the thermal efficiency is 1 minus QL over QH. That's for reversible, irreversible. And if it's reversible, then we can replace the ratio of Q's by ratio of T's. And that gives us the maximum thermal efficiency. This is another big deal. And it only depends on the temperature of the sink in which you have to throw some heat away out of the cycle, and the temperature of the source, the high temperature and low temperatures in absolute. So often 300 Kelvin for atmospheric temperature. And if you have a 600 degrees C heat source to provide or feed your heat engine, you could get a maximum of 50% thermal efficiency. Meaning you can't do anything but throw 50% of that heat transfer from the heat source to the environment. That's a limitation of the second law. You can't move it beyond 50%. That's the upper limit. What happens if your heat source is 900 Kelvin? Well, you can do better. The maximum is 67%. But notice it has tremendous improvement in efficiency, going up dramatically as you increase the temperature, but then it tapers off, and this 300 degree change going from 12 to 1500 only gains you another 5% added. Where if you went from 300, the first 300 degree temperature was 50% increase. See, so going from 0 to 50% versus increasing from 1200 to 1500 only increased by 5%. Now, this plot again is little trivial, but it's really insightful. When you think about alternative energy sources, you think about, oh, we're going to get energy out of the hot ground and it'll be a geothermal well and we'll make a lot of energy off of that. A lot of times our renewable energy sources or unique or alternative energy sources don't have a high temperature, especially compared to burning natural gas or burning some gasoline. That you can get very, very high temperature. Often you have to reduce the temperature at which it's burning because it creates a lot of NOx. It gives you emissions problems, or you have to reduce the temperature because it makes you, the metallurgical considerations, the equipment can't handle the high temperatures. But in the combustion, you can go very high temperatures. But if you go to a renewable or alternative energy source, it may be where the people want to have let's say a 400 Kelvin heat source. That's water boiling temperature, roughly a little over 100 degrees C. That's pretty hot. Hey, I should be able to make a lot of energy out of that. Do the math with this equation. What percent of that energy are you really going to make? It'll be right at 25% when it's 400 Kelvin. Meaning 75% of the heat you intake from the hot source is going to be disposed of to the environment. And only maximum 25%. So when the delta T gets smaller, you're limited. You really can't convert as much of that heat transfer from the hot source into work. That's a surprising result. All right, You can also then do the Carnot refrigeration and heat pump cycle. I think I did this last time. Did I not?
We got as far as the ground.
Okay, well, let's go ahead and put it so you have a temperature high and the temperature low. And what you have is a cycle operating, a system operating in a cycle, continuously bringing in Q sub H. Whoops, this is for refrigeration. We're bringing in Q sub L and dumping off Q sub H, having to feed it the work. That's how a refrigeration or heat pump system works. And so for the coefficient of performance for a refrigeration system, it's what you desire, a large amount of cooling, divided by what it costs, a large, not large, but hopefully minimum work input. From the first law, this work is going to be QH minus QL, true? Conservation of energy. So you can replace this by QL divided by QH minus QL, which is 1 over QH over QL minus 1. And now, if it happens to be reversible, you'll get the maximum COP for the refrigeration system. And that maximum can be related to 1 over TH over TL minus 1. Or you just unravel, you get TL over TH minus TL. That's the COP, coefficient of performance, refrigeration system maximum. There. Instead of low temperature, cold temperature. Sometimes L, sometimes C. Likewise, you could do the same thing for the heat pump. It's just what you desire for the heat pump. The COP for the heat pump is, I want a large QH for the same W in. And if it's a maximum, you can replace the ratio of Q's with the ratio of T's, and you get this similar result. Clicker question. A reversible power cycle indicated by the subscript rev and an irreversible power cycle indicated by the subscript IRR for irreversible operate between the same hot and cold thermal reservoirs. So I have a thermal reservoir, T sub H. I have another thermal reservoir, T sub L. And I put in one system here and I put in one system there. They're operating in a cycle. The purpose, these are power cycles, so they ingest QH. They ingest QH. And they try to convert as much of that into work as possible. But then they have to throw some QL away. And what we want to do is we want to compare one that's reversible with one that's irreversible, IRR. So how does the thermal efficiencies compare? Does the thermal efficiency of the reversible system, is it greater than the thermal efficiency of the irreversible system, or is it equal, or is it less, or it could be either A or B, or it could be either A, B, or C. So now that I've read the question, there you go. Got 30 seconds. And so the thermal efficiency of a reversible power cycle is the highest that you can get. And if you have any irreversibilities, it will degrade the system's performance, won't it?
It's a Carnot corollary.
It's Carnot corollary, one of the Carnot corollary, right? I'll modify this. Irreversible power cycle, or reversible rev and irreversible power cycle operate between different hot and cold thermal reservoirs. So this one right here has a thermal reservoir. This one has a thermal reservoir. There's TH there and TH there. They're different hot thermal reservoirs, and they're different low temperature, TL and TL. Those are different temperatures, okay? How do the thermal efficiencies now compare? Let me ask a clarifying question. Is this temperature the same as that temperature? Yes or no? No. Is this temperature the same as that temperature? Yes or no? No. All right, now I've helped you with the clarifying question. You still have 30 seconds, 27 seconds. All right. Well, could this one, for this high temperature right here, could that be maybe 400 Kelvin and this one 300 Kelvin and this one 300 Kelvin and this one 1500 Kelvin? Would that be possible? It's different. It could definitely be possible. And in that case, what do you suspect? Even though this one may be irreversible, it has such a huge delta T to work with that it may give a better thermal performance, better thermal efficiency than even the reversible one. Okay? As long as they're different. It could be this way or that way. True? All right. So we have a Carnot power cycle. It's conceptual. But what goes inside this box to make it work? Is there any sort of way that it could actually physically work in practice? How might it be possible? Well, it is possible. And so it's possible by a few different schemes. The most common is to say what we're going to do is we're going to analyze the Carnot power cycle using the working fluid being an ideal gas trapped in a piston cylinder assembly. And what it is we're going to undergo processes 1 to 2, 2 to 3, 3 to 4, 4 to 1. That makes our cycle. And every one of these processes is internally reversible. You can't have friction. All right? It's going to be internally reversible. And also, whenever you have a heat transfer with the surroundings to one of those thermal reservoirs, the high temperature reservoir, the low temperature reservoir, you're going to have a reversible heat transfer, meaning that the temperature of the working fluid is the same temperature as that thermal reservoir as they're interchanging heat transfer back and forth. You say, that's impossible. No, it's not. Listen, let's go through it. First of all, let me sketch on a PV diagram two things. A pressure volume diagram. If it's an ideal gas, is PV equal to RT true or false? If I can draw this a line where I have TH, and it's a constant, that would be an isotherm. What does an isotherm at high temperature look like for an ideal gas on a PV diagram? Like that. This is TH. Mathematically, that's called a hyperbolic function or something like that from your algebra class way back when. If somebody said, I want you to plot y is equal to a constant over x, that's what it would look like on a xy plot. And it asymptotes back to both axes. And if they change the constant, it just pushes the curve further out or tucks the curve further in. Let's change the constant. We say PV is equal to RT, this time lower temperature TC instead of high temperature TC, right? What does that curve look like? It has the same shape, but it's either pushed further out away from the axis or tucked in closer to the axis. Which one would it be? Closer in. And so there's a curve of constant temperature TC. All right? Great. Now we have that foundation laid. Let's take a look at the process 1 to 2. Gas expands isothermally. So what do you mean isothermal expansion? At constant temperature, TH, it's going to expand while it's being heated, while it's receiving heat from a high temperature reservoir, QH. So maybe I put state 1 right here, and I'm going to expand to state 2 right there. That's how it would happen on a PV diagram. What's happening during the process 1 to 2? Well, as your gas, which is the system that you're analyzing. It's a closed system. It's doing boundary work, pushing back that piston. So the work is going out of the system. It's doing work on the surroundings. So as it expands, the work is positive. Hence, you bring in some heat to keep the temperature constant, to keep the internal energy constant during the process. So sometimes they'll say, oh, right here we're bringing in heat into the cycle, QH. What happens from 2 to 3? Gas expands, but now it expands not isothermally, but it expands adiabatically. I don't like these words. What does adiabatic mean? No heat transfer, well insulated. Q is 0. So if it's now going to continue to do boundary work, but no heat's coming in, the temperature is going to go down. The temperature is going to drop. And you expand it just enough so that it drops down to the magical low temperature TL. So that's expansion dropping to the next isotherm, that lower isotherm TL. Sometimes I put C, sometimes L. I'm sorry about that inconsistency. Let me try and put L there for low. All right. But hey, I put TC right there. Okay, fine, put TC everywhere. I'm sorry. Some books and sometimes it's cold or low. Either your choice. Now, you have to get back to 1, so let's start compressing. And if you have isothermal compression, that means as you compress, you have to cool it off. Otherwise, the compression would heat it up, and you're going to have a QC out of the system, cooling it off from 3 to 4. And then what happens 4 to 1? Adiabatic compression. Boom. Back up to 1. See that? So that's our cycle on a PV diagram for an ideal gas undergoing Carnot power cycle. Make sense? That's one way conceptually you could say, yeah, this system could work. Could conceivably work. Air acting as an ideal gas with the molar mass of ideal gas given, specific heat constant pressure given, specific heat constant volume given, within a piston cylinder assembly executes a Carnot power cycle. Property values are shown in the table. Here is state 1, 2, 3, 4. Here is the temperature. Can you tell me process 1 to 2? How would you describe the temperature change in the process from state 1 to 2? Isothermal. Temperature's constant. All right. How about for the process 3 to 4, looking at the temperature? Isothermal. How about 2 to 3? That's going to be that adiabatic. And then 4 back to 1? Adiabatic. All right. Now, take a look at the pressure, but jump over to specific volume. I know these are kind of weird numbers, but what's happening going from 1 to 2? Look at the specific volume. Expansion or compression? It's expansion. Right? And then from 2 to 3? Expansion. And then 3 to 4? Compression. 4 back to 1? Compression. And then the pressures help you on the y-axis. So we can make and refresh ourselves on that PV. And this line right here would be a constant temperature of 600 Kelvin. This line right here would be a constant temperature of 300 Kelvin. And I know I'm not drawing at the scale, but those volumes you could try and draw at the scale, but it'll be a little expansion from 1 to 2, a great big expansion from 2 to 3, a great big compression from 3 to 4, and a little compression from 4 back to 1. Or maybe I really distorted it, sorry. But there's the diagram. You're bringing in heat right here, Q at the high temperature, rejecting heat into the cycle, Q at the low temperature. They put this little dash marks like that to indicate what for the process 2 to 3 and 1 to 4. Adiabatic, no heat transfer, as if that's insulated. Has a little sign in engineering for insulation, right? Okay. So we sketched it on a PV diagram. We want to evaluate the heat transfer and the work transfer for each process. There's 4 processes. I need 8 answers. I need 4 Q's and 4 W's. Now, why do they put the lowercase q and the lowercase w? Look at the units. It's per unit mass. So let's write the first law for the process 1 to 2. Q 1 to 2 in minus the work 1 to 2 out is equal to U2 minus U1. Neglect changes in kinetic potential energy. Thumbs up if you agree. Good first law? All right. What about either term A is 0, term B is 0, or term C is 0? Clicker question. Tell me which one is 0. For this problem, for the process 1 to 2, either Q 1 to 2 is 0, work 1 to 2 is 0, or the change in internal energy is equal to 0. Which one? Well, let's see. Is the temperature at 2 equal to the temperature at 1? It is. And if you have an ideal gas, this is an ideal gas, not only is PV equal to RT at all times, but U is a function of temperature only at all times. So that's true. That's true. So, C. That's equal to 0. So, Q 1 to 2 is equal to work 1 to 2. That's the result from the first law for the process 1 to 2. I think I can calculate work 1 to 2 from first principles by the integral PdV. And if this is always true, then P is equal to RT hot divided by V dV. Did I do that right? I substitute P is equal to R, the high temperature divided by the specific volume. During that process, R is a constant. I can pull it outside. During that process, temperature hot's a constant. I can pull it outside. I have to do the integral of 1 over V dV. Professor, I don't like math. Well, that's just... Yeah, math doesn't like you either. That's right. That's a good response. All right, so the work 1 to 2, I have the specific volumes right there. The only thing is the student after the 9 o'clock says, well, how'd you get that R? How do you get that R? R bar, 8.314 divided by the molar mass for air. All right. You sure could. You could put there P1V1 or P2V2. You could definitely do that. That's insightful as well. All right? So the student just said P1V1, natural log of V2 over V1, or P2V2, natural log of V2 over V1. Either one of those work. All 3 of those will work. And we get that the work 1 to 2, I'm just going to put it up here, is 22.011 kilojoules per kilogram. Why so many digits? Well, I don't want to have a problem with round-off error. And then guess what the Q is? 22.011. I go back to the first law. Okay? Now,
Can we just put it 4 to 1?
4 to 1 now? Let's do the process 2 to 3. All right.
Like since we know that they're the same, since they're adiabatic, can we just fill in the table? Or
Yeah. No, fill in the table. When I ask you to put in numbers in a table, put them in the table. I know where to look for the answer in the exam. A lot easier to grade and everything. But if you want, then you could actually put it like 1 to 2, put the answer here, and then put the answer in the table. All right. But let's do process 2 to 3. Q 2 to 3 minus work 2 to 3 is equal to U3 minus U2. True? All right, clicker question. Is this A is that equal to 0? Or B, that term equal to 0? Or the change in U equal to 0 for the process 2 to 3? And now I give you 30 seconds. All right. Pretty good, huh? We said it was adiabatic, true? There you go. So that's equal to 0. Now, how do I get the work 2 to 3 then? Is that just going to be, is the work 2 to 3 equal to minus the specific heat constant volume T3 minus T2? Is that what it is? And then they gave me the specific heat constant volume right there. Yes? Yes, it is. And when we calculate then, this is 0. And the work 2 to 3 is 215.4. 10 times bigger than the work 1 to 2. Like 215 compared to 22. All right. Then we go 3 to 4. It's a lot like 1 to 2, but it's a constant temperature at the low temperature. Just let you, I'm going to put in the number negative 11.006 and negative 11.006, and then do the process 4 to 1. It's a lot like the process 2 to 3, and you'll find that it's adiabatic, and you find negative 215.4 kilojoules per kilogram. So in interest of time, I think you can figure out the other two. They were just like the previous two processes. Now, well, what's the thermal efficiency of the cycle? Is it the net work out of the cycle divided by Qn? So if I sum this column right here, what do I get? Is that the net work? And it's 11.006. That's the sum of that column. Kilojoules per kilogram. So the thermal efficiency is 11.006 divided by Qn. Where do I have Qn? Only 1 to 2. So I divide by 22.011, and the thermal efficiency comes out at 50%. Somebody says, is that consistent with the equation that you just showed a minute ago, which was for any Carnot heat engine, the thermal efficiency is equal to 1 minus TL over TH, 1 minus, in this application, 300 Kelvin divided by 600 Kelvin, which is, this is one of those surprising. All of that work, if I didn't drop any digits, I kept all my digits, will get the same answer as that shortcut, 1 minus TL over TH. It's pretty profound, isn't it? Yeah, pretty surprising. I remember when I first was like, what? My jaw dropped. Does this really work? Magic. Somehow it's magic. I don't know. But no, it gives you the 50%. The Carnot power cycle can most often be analyzed with an ideal gas as the working fluid trapped in a piston cylinder. But you can also put in a working fluid, it's a lot of work, that changes phase, that boils and condenses. Just all the heat has to come in at the high temperature. And all of the heat has to be rejected at the low temperature. So you can do it for a closed system with a fluid that changes phase. You can also do it with an open system, conceptually, an open system, meaning that it's going to flow between components in a loop. And here's one. It flows from a boiler to a turbine to a condenser to a pump. And in that boiler, all the heat's added at that high temperature. Constant pressure boiler, going from saturated liquid to saturated vapor. If I put that on a PV diagram, pressure volume diagram, it'll be going from saturated liquid to saturated vapor, all at the same temperature. But then I have to figure out how to expand through a turbine. You don't quite have the entropy concepts needed for that, but it would look something like this, down to 2, and it would be a two-phase mixture. And then you'd put it through the constant pressure condenser, in which you're going to reject some heat, but you're not going to reject it to get saturated liquid, because you need a very special pump that doesn't exist in the world, but conceptually it's on our paper, that then would ingest it at state 3 and kick it perfectly back up to state 4. But these tools we'll revisit at the beginning of chapter 8 when we get there, after we have entropy. So when you have a Carnot power cycle, it's often described closed system, piston cylinder with ideal gas, but it could be piston cylinder with phase change material like water or refrigerant. It could also be an open system that's like water or refrigerant changing phase. And yes, there's other systems that you can analyze, but these are the big ones. Let's move on. Let's talk about Carnot gas refrigeration and heat pump cycle. It's just the opposite. So if I said on a PV diagram with the high temperature doing ideal gas and a low temperature right here, so I have the TH and the TL. If I took and instead of going where I'm expanding at high temperature, if I adiabatically compress at high temperature, adiabatically expand, and then isothermally expand. So if I go 1, 2, 3, 4, I'm going now not clockwise, but I'm going counterclockwise. That's a refrigeration cycle. It'll have network into the cycle, and it'll pump the heat up from low temperature to high temperature. And that's how you could get a Carnot gas refrigeration cycle to work. This person, Clausius, lived a long time ago. I showed this slide last time, but he really laid the foundation for this property called entropy. Next chapter. But what it allows us to do is quantify and get the plug and chug on the second law of thermodynamics. Really quantify the second law. Otherwise, they were saying, well, that's impossible. I'm not certain exactly how and why, but I know it's impossible from experience. And there's limitations. He actually allowed us to quantify it a lot better. But it is a little difficult to understand. So the key part to end this chapter is called the Clausius Inequality. It's the basis by which we introduce the new property entropy, the next chapter. Let me try and outline it. I have a heat engine operating between high temperature, low temperature thermal reservoirs. We already discussed that if it's a reversible heat engine, then the ratio of QH divided by QL can be replaced by TH over TL if it's reversible. True? Let's just rearrange this a little bit. QH divided by TH equal to QL divided by TL. True? Did I do the math okay? This is only for reversible. And then I'm going to do this. Negative equals 0. And what he said, he looked at this, and he's a genius. But we just have to figure out, what did he say? Not try to think, oh, that was trivial. No, this is not trivial. This is hard. He said, this looks like something that flows in with the high temperature heat flow in. It looks like something flowing into the system. And this looks like something that flows, because of the negative sign, out. And it looks like whatever flows in flows out. And that's the perfect system. But he then made the brilliant deduction that, well, what happens when it's not reversible? Well, then what flows out has to be greater than what flows in, so that this has to be less than or equal to 0. It becomes an inequality. And so the fancy way of writing that is, he says, the integral, the summation over the entire cycle That's that circle right there. The integral over an entire cycle of all the heat transfers in divided by the boundary temperature in which it comes into the system. That integral is always less than or equal to 0. It's equal to 0 if I have a perfect system. If I have any irreversibilities, it's less than 0. That's the Clausius inequality. Now, I remember when I was a student learning algebra, they would give you these inequality equations. Man, they were hard. So what did you try to do? Turn them into an equality statement with an equal sign, not an inequality, right? So what you do is you say, aha, I'll turn it into an equation with an equal sign where I know this side has to be negative. And one way to make it negative is like put negative lambda squared, something like that. Maybe that appeals to you from your math class. You always do that. You say, I know it's negative, but I'm going to put a negative a lambda squared. This is always positive. Well, here they just put negative sigma of the cycle, and they talk about it. They say, you know what? If it's really, really far away from 0, it's a really large negative number, there's a lot of irreversibilities. If it gets closer and closer to 0, approaching in the negative direction, then there's less irreversibilities. And in the limit, man, if I could just get to 0, I got rid of all the irreversibilities. I can't do any better than that. So by introducing it this way, then they have a test for the second law. They say, look at the value of sigma of the cycle. Sigma of the cycle can be interpreted as the strength of the irreversibilities. Is there a lot of irreversibilities? Sigma's large. But anyway, if sigma is greater than 0, there are irreversibilities. And if it's much, much greater than 0, then it's a lot of irreversibilities. If it's equal to 0, you've gotten to the perfect system. You can't do any better. It's all reversible, right? And if somebody gives you a sheet of paper with a new design on it, and if you check it and find that sigma is less than 0, you can conclude you don't want to invest your money in that energy scheme because it's impossible. So this would be a violation. What would it violate? The second law of thermal. And there's a test for it. Okay? So this is the Clausius inequality. Oh, I have some more problems for you. Clicker problems, huh? We have a power cycle operating between two reservoirs at 300 Kelvin and 900 Kelvin. So I'll just sketch it. TH is 900 Kelvin. TL is 300 Kelvin. And it's a power cycle, meaning that I take heat in, QH, and I have to throw away some heat, QL, and the goal is to convert as much into network out. The cycle rejects 400 kilojoules and produces a net work transfer of 600 kilojoules. How does the cycle operate? Does it operate reversibly, irreversibly, or is the cycle not possible? All right, let me go ahead and try and answer it. So somebody, when you get the 900 and 300, I could calculate the maximum thermal efficiency, the Carnot thermal efficiency, 1 over the low temperature, 300 over the high temperature, 900. 3/9, that's 1/3. So this is 67%, 2/3, right? Now, I could say, what is the actual reported on the numbers? Well, what is the workout? 600 over the heat in. Well, the heat in, I got to do energy balance quick. What is QH? How much is it? 1,000. It's 1,000. Can you see it's 1,000? So it's 1,000. So guess what the actual reported thermal efficiency is? What can I conclude? It's irreversible. Now, the other way of doing it is go through Carnot's inequality. So we have the integral over the cycle of the Q over TB. Let's put the del there. And that has to be less than or equal to 0, but we put it equal to a negative sigma. And so this is another way to solve the same problem. Let me do it, please. we're going to have QH coming in of 1,000. Let me do it in 2 steps. QH is positive n. We divide it by TH. Then we have a negative QL going out divided by TL, and that's equal to negative sigma. So we put in 1,000, we divide by TH 900 minus, we put in 400, we divide by TL 300, which is 1,000, what is that? 10 over 9 minus 4 over 3. Can somebody run that for me? 0.22, negative 0.22? Good enough. So guess what sigma is? 0.22. Hence you conclude that there are some irreversibilities. So same bottom line conclusion. And so it was B. Thank you for your attention. We'll see you next time. I'm sorry. 1,000, 600 and 400 go out. 600 out, 400 out. So what comes in is 1,000. Yeah.